This is our presentation for the middle school thermometer training box by Ethan Brees.
Ben Bame.
Gabriel Sanchez.
All right, so for our project goals, we want to introduce middle school students to the fundamental electronic concepts. And so to do this, we designed and built a temperature-activated LED bar graph thermometer. This is to provide a hands-on, engaged learning experience. And then our deliverable was to deliver a functional trainer box for classroom demonstrations. So why did we choose a temperature display trainer box? We feel like this visual feedback makes the temperature concepts tangible to students, easy to understand. It uses widely inexpensive components that are also pretty easily available. It reinforces some core concepts like voltage dividers, comparators, and calibration. And we also feel like it's scalable, can have different complexity levels for different grade levels. So our design overview, we have an LM35 temperature sensor that outputs 10 millivolts per degree Celsius. It has signal conditioning, so a voltage divider and LM741 bar graph driver. We have 10 LED bar. Our 10 LED bar indicates the temperature range between 30 degrees Fahrenheit to 120 degrees Fahrenheit, and then we have a 9-volt power source.
So here's our overall design. We can see our LM741 op amps in the middle. They're all set up as comparators. So they take the voltage that the LM35 outputs. And then at the top right, we can see a little voltage divider that takes our 10-volt input and drops that down to 1 volt for the bottom row of voltage or bottom row of resistors as another voltage divider as all of the comparing inputs. So as if the voltage in the bottom resistor network is larger than the LM35, the LED light will light up from right to left. Here's our simulation that shows the exact same thing as our design, just using this for proof of concept before we started building the circuit to make sure everything would function properly. Here are our simulation results. We can see as the voltage network or the resistor divider network would be greater than the LM35 output, our LEDs would go and turn on. We can see that through all of our 10 LEDs through our DC sweep analysis.
Key components that we had were the LM35 temp sensor, and then as shown in the design, we had 10 LM741 op amps used, and then for the 10 op amps, we also had 10 LEDs for those as well. We also had a 100K ohm potentiometer, including the breadboard resistors and wiring as well. And then an optional thing that wasn't needed necessarily was the solder kit. And then the total cost of everything came out to 38 and 57 cents. That is including the optional tools. Without that, it would have been $23 and 57 cents. So, and then our week by week design process, we started off week one by planning and figuring out what we were going to basically do our project on. With that, we did decide which parts we were going to use after we found out that we were going to use the thermometer as our design. And then with week two, we built the sensor circuit and had the initial testing for that. And so we started with that whole process. And then in week three, that is where when we found the first time that we built the circuit, it didn't work as intended. So we had to calibrate that and fix everything, almost rewire it, but we didn't have to. And then in week four, that's when we did the final testing and documentation. And that's when we had the design set up as we needed. And we have the demonstration further on in the slides as well. And then these are our circuit calculations. On the right, we have the voltage divider for each resistor. And then on the left is pretty much just a hand-drawn schematic that we had basically based off our LT Spice simulation. And that's pretty much it for that one. And then we started off with our simulation verification by doing the LT Spice DC sweep, which was shown before. And then after that, we did replicate it in Multisim just to cross-reference and make sure the graphs and everything matched up, in which they did. And then not only that, but both simulations matched our hand calculations as well, and they were within a plus or minus 2% error value as well. And then we were able to validate the design for actually building it as well. And then pretty much our thermometer trainer box functionality is basically just a plug and play module for the classroom use for the kids. And then the thermometer does respond in real time temperature changes. So we also have a safe low voltage operation for the not for the system as well, so kids are able to use that and look at it as well without getting hurt. There will be a transparent cover which shows the circuits as well, so that they're able to learn basically what is going on the inside as well.
So our demonstration plan for if or when we present this to middle school students, we'd start with a brief intro to show the LEDs lighting up, reacting to the warm and cool temperatures. And we'd really highlight it as more LEDs would turn on the hotter it got and then turn off as the temperature decreased. We would invite students to predict an LED count at a given temperature. So 30 degrees Celsius, how many lights do you think would turn on? And then we would also discuss practical applications such as HVAC, appliances, or uses in science labs. So we feel like this has a good educational impact. It's a hands-on activity which solidifies theory through experimentation. It encourages curiosity in electronics and STEM careers. Some future enhancements, we feel like a digital readout, some data logging, or maybe a 3D printed case could also adapt this project for other sensors like light, humidity, or sound.
Here's our circuit demonstration. So we can see as the circuit turns on, the bottom three LEDs will gradually start lighting up as the circuit gets warmer. It does end around 30 degrees Celsius, which is about 86 degrees Fahrenheit. We contribute that to being slightly warmer than room temperature because the components would warm up as the circuit is in operation. Overall, our circuit did function as intended, lighting up a new LED about every 10 degrees Celsius. Thank you.
Thank you.